Is it recording? Thank you. Now, welcome. This is week number 8. And we have gotten to the chapter Lagrangian and Hamiltonian field theory. We started all this by writing on field equations, and then last week we came up with Lagrangians. So the Lagrange equations for those Lagrangians gave us these. They gave us the equations of motion from before. These are the Lagrangians. For the real and the complex scalar field, it's very similar. There's a conventional 1/2. The overall factor doesn't matter because you only want to vary the thing in the end, and the variation is set to 0, so the factor doesn't really matter. But the conventional, because if you differentiate with respect to phi, then you have one derivative here, one there, and so the half goes away. Here, if you differentiate with respect to phi, you only have one place where it hits. This is the Lagrangian for the Weil spinor, this is for the Dirac spinor, and this is for the vector field. You may, there's a square missing. You may, of course, set m to 0 everywhere. Then you have the massless vector field for Maxwell theory. Here you have a massless Dirac spinor. So I those are reasoning of a massless Weil or that is m's. And then we saw something very funny or strange happening with these two terms. Because the sigma 2 looks very innocent, but it is anti-symmetric. The sigma 2 is the second Pauli matrix, which is this thing. So it's anti-symmetric. The sigma 2 transpose is minus sigma 2. And then this term here, say, I'm picking this because there's no complex conjugate, so it's easier to so this is the transposed psi 1, psi 2, the two components of my two-component Weil spinor, put into a row. Then comes this matrix, and then the same Weil spinor but vertically. And if you multiply this out, then the sigma 2 goes to the top, the psi 2 goes to the top, the psi 1 to the bottom, and then they meet in the other way. So this means the psi 2 and psi 2, psi 1, and the first one gets a minus I, the second plus I, and then at first sight you'd say that is 0 because it's the same with the opposite side. And then we said no, we want to keep it, and also this is just, I mean, at first you'd say it probably wants to tell me I can't give Weil spinors a mass, right? Because it's 0, you try hard and it doesn't work. So that would be a possibility that you couldn't. But as we go along, we'll see at other places this coming up. And this means that they anti-commute. If we have to just postulate, we have to just define our fields, this one and this one. Here we won't see it at this point, to anti-commute. So now I'll tell you a little bit about these anti-commuting numbers. And this is called Grassmann numbers, Grassmann variables, or the Grassmann algebra. So we are coming up with numbers that satisfy. If you turn them around, then you get a minus sign. So we want to define this as minus psi 1, psi 2, so that they do cancel by that out. And then we have minus 2i, and it's non-zero. And then we're happy. Yeah, let's leave it at this and do some math. You start by introducing some symbols. I run from wherever you want, 1 to n, say, and these are really just symbols. So Grassmann numbers or Grassmann variables. But even though people call them Grassmann variables, this is not some xi where you can plug a number in. This is not a real or complex number, it's a simple. Symbols. And you take these symbols as the basis of a vector space. So you want to be able to multiply them by real or complex numbers, lambda, and you want to be able to add them. So I don't know, like plus mu theta j. Now you have a vector space, you can multiply by numbers and add them. And we want to have an algebra, so we also want to multiply them. And since these are just symbols, we don't really know how to multiply them. It's a little bit, yeah. We leave it at this. So this is now a combination. You can't simplify it any further. Like if it was real numbers, you would be able to compute the product, 2 times 3, and then you write a 6. But here it's what it is. With the agreement, if you change the order in such a product, you get a minus sign. And we can write this thing a little bit more fancy as the anti-commutator. So that's the one we had already before. It just means this order plus the other order. So bring this to the other side. So if I use this property, yes.
And does that mean that if we look at 1 and 2, that phi 1, phi 2, that we can compute the product of the both because they're class 1 numbers? We have to say like that? Yeah.
Yes. Since this is all variables, you don't really multiply these things anyway. Yeah. By the way, this index, yeah, this is also one index. But these things have more indices, right? So they are psi x's. And if you the connection from here to here is also to let this index I. So the index I goes to this x. So when we have theta I, then we'll have the psi of x, and then maybe extra indices. So for every, this is like a discrete, is like a continuous label. We have Grassmann numbers for all the positions. But let's just have some fun with this finite dimensional space for starters, and it's nice and simple. And now I want to look at what this means if I said I equals j. There's no sum now, it's just theta I. And since they all anti-commute, they anti-commute with itself. So theta I. I have turned it around, although you don't see it. So now it's basically the square. You can be very formal, bring this to the other side by adding it. I know how to add numbers. Then I have 2 of them, and divide by 2, or multiply by half is also, and then you just end up with theta I squared is equal to 0. So every of these numbers squared to 0. This is what you can actually simplify. Here you can simplify. You can simplify it the same. Theta 1 times theta 1 is 0. So that makes them super easy. For example, if you have you can write down functions. And if I have a function of one single Grassmann variable, then it has a very simple expansion in terms of the thetas. So you could have the term that doesn't have any theta in it, so that would be a complex number, say, and then you can have a number times theta, and you cannot have the theta square in this expansion. It's like a Taylor expansion, because that's 0, there's nothing, this is all. The expansion in terms of theta is very simple. If you have 2, theta 1, theta 2, you have nothing, or the first, or the second, or both, theta 1, theta 2, in an order that you like. You don't have to write the other order because you can write the other order using this back to this order and with the minus sign, but this is just a new coefficient, so that's already the expansion. If you have 3, you can get single ones, 3 different pairs, and all 3. But none of these things can have one of the Grassmann numbers twice. And so I guess because you can consider functions of these Grassmann objects, people call them Grassmann variables. So it's a variable for this function, but it's not that you can substitute in anything. And now that we have functions, we want to take derivatives. So we want to take a derivative with respect to these variables, so the function differentiated with respect to this. And then, of course, we want to define that theta I differentiated with respect to theta I is just 1. And theta I with respect to another one is nothing. So let's write it shorter like this, like for real variables. And now we have all these derivatives. The funny thing is, the derivatives also have to anti-commute. So theta I, so 1 theta I d by d theta j has to be minus d by d theta j d by d theta I. Why is that? Let's take the derivative. Just an example, I take theta 2 theta 1. I write it in this order because then the derivative hits the 2 without doing any funny business. And then we theta 1. And this is, of course, 1. And then these two hit each other, and that's just 1. And now I know if I turn them around, then I get a minus sign. So I have certainly, with the rules we set up, this equality. This is equal to this with a minus sign. And now I can try both things. So either I just swap them around with no extra minus sign, then we have d by d theta 2, d by d theta 1, theta 1, theta 2. That's in the case they would just commute. Then this is a 1, these two are 1s are totally with a minus sign, and it's not the same. That's bad. So this case is if these from mute. And the other one will work, right? So if I have this minus sign that I here want to have, then I get this plus. Now turning this minus into a plus again, you're gonna have d by d theta 2, d by d theta 1, theta 1, theta 2, and that's 1, and then so that's true. At least it's consistent. So we have the variables anti-commute, the derivatives anti-commute, and if one hits its own friend, we have sometimes a delta, sometimes a 1, sometimes a 0. All of this can be summed up in this. The theta I, the j is 0. The d by d theta I, d by d theta j is 0. This is the anti-commutation, and then we have a d by d theta I with theta j. So the derivative with the Grassmann number, this is delta ij. So let's be a bit more explicit. If this is d by d theta 1, theta 2, then I can let's say this is as an operator and it acts on something else. F of stuff. Then this is, it jumps through the theta 2 with the minus sign by the, I don't know if this helps. Maybe we do I and J. Let's write exactly this down. D by d theta I theta j plus theta j theta I is equal to delta ij. And you're supposed to think of we're acting on something, maybe an F, an F, and an F. And if they are different, we don't, and now I bring this to the other side. So d by d theta I, theta j f is equal to minus theta j d by d theta I f equals plus I j f. So I just want to make this a little more explicit. And I have spelled the anti-commutator out and brought this to the other side and acting on a function f. So if now the derivative hits this product, then this is basically a Leibniz rule, except for the graded one. It can hit the first term. If it hits the first term, it gives you a delta ij, 0 or 1, depending on whether it's the same or not. So that term, the first in the product should be the first one, times f, or then it goes to the f, further to the f, but with an extra minus sign, because it has jumped another Grassmann variable. Does that make sense? So if I do say I do this, d by d example, another example. D by d theta 4, I think I picked. Theta 1, theta 2, theta 3, theta 4, theta 5, theta 6. I want to compute that. You don't know why, but it will, it will be. So then nothing happens here. Theta 1 and theta 4 is 0, but I have to jump to get to my 4. So how many times do I jump? I jump 1, 2, 3 times until I'm here. So I'm getting a -1 3 times. I'm jumping, and then I have the derivative at the right place where I want it. It would be plus, and then the other ones, but there's nothing coming. I'm saying here's it's done. I don't prepare for another function that depends on theta 4 to be there. This is just it. So there's no other term, and that's just 1. So I get minus theta 1, theta 2, theta 3, theta 5, theta 6. We will come back to this in a minute. So happy so far? We have just an anti-commuting stuff. And we can take derivatives, and then we have to be careful when we take derivatives, the product will get these minus signs. Yes.
So this anti-commutation rule with the derivative and the variable, it's just stated. We didn't prove this, right? So it doesn't follow from the other stuff, or did we?
It does. No, we didn't.
But is it
How
possible? So
here, sorry, like in this example, this wasn't, I don't know if this was a proof, but this is something that made sense. Now we want to show, I guess, that d by d theta 1 with theta 2, that this anti-commutes. This is what we want to show. And I guess we have to come up with an example. So is this true? Is this consistent? This is what we're going to show. So I guess we look at this example where we have the theta. We need to insert something that we can actually differentiate with respect to, right? So I'm inserting this. Then I know that is just theta 2. Then I know if I flip the two things, so on the other hand, minus d by d, theta 1, theta 2, theta 1. And now I'm asking, do I get a minus and a plus sign if I pull this on the to the theta 2? And then I can play the same game. If I didn't get a minus sign, then I would end up with minus theta 2, which is different. If I get a minus sign, then this gets canceled again, and then I get the theta 2, and it's at least consistent. So proof by example. I'm just giving all those rules, but they are nice to remember. Everything anti-commutes. The objects, their derivatives, and even derivatives with those objects, except for when they are the same, then you get an extra one. Now, Taylor expansion. Since we will be doing Taylor expansions a lot, we have done this for the variation of the action of the Lagrangian to get our Lagrange equations, and we'll do it today for Noether's theorem. So Taylor expansion with these Grassmann objects. So it's simple enough because my functions are very simple, but I have to be careful about the order. If I have an ordinary Taylor expansion, ordinary means with respect to a real or a complex variable, you write f of x is equal, and then you get all these terms over n factorial, and you maybe you like to write them like this. X n, and then you set the x to 0, and then multiply by x to the n. So I'm expanding about x equals 0. And the variables go to the right of this. Or maybe you'd like to write it the other way. We know the n factorial, x to the n, d n f x. So here. And it is the same thing. How about our funny Grassmann objects? If we have a function f of theta, and I just want to make it more complicated, I need to have anti-commutating stuff around. So let's say example. Example, not expansion. And I want this to be 1 plus theta 1 theta 2. I think of it as a function of theta 1, but there's another guy, theta 2, hanging around. Then the first term is just the 1. So actually now I did put a value in there, right? I guess 0 is fine. Just kill this thing. I guess that's okay, because now take the derivative with respect to theta 1, then that's constant. This leaves us at theta 2. And now there's no higher, like all this big sum goes away because it's all intercommutative, it's all finite. If I put these things together, then I have f. So how do I get my f is theta 1 back? If I write x plus, so then I want the derivative df d theta 1, that's the theta 2, but it should be on the right, so I have to have this theta 1 in the front. And then that's okay. But it's not okay. So that's okay. But f of 0 plus df d theta 1 theta 2, this would be 1 plus theta 2 theta 1, which is not the same as what we wanted. So this combination is 1. If I have the deviation from the expansion point to the right of the derivative, I get the wrong order, and that is of course minus theta1, theta2, and it's not the f what we started with, but if you do it in this way, you get 1 plus theta1, theta2, and that is indeed the thing you want. So now we have to be careful. We have to stick to basically this thing. If the variables I'm writing the Taylor expansion for, then you have to put the deviation to the left. And the reason is because these derivatives come from the left, as you see here. Now, since I like this better, and for all these bosonic computations we have done, we kind of always write it like this: derivative and then the variation. And this always looks like this. We will define a derivative from the right. Just for those Grassmann derivatives, will make a difference between differentiating from the left and from the right. So define this thing, dr by d theta I of something, and that is defined as, and now this is a bit funny, from the right to the left. I'm defining something by something that isn't defined, except for, you know what it is, it's coming from the, you've seen this now, the content, even bosonically you write this. Yeah. If it looks nicer, you sometimes see this with 2 errors, first there and then minus this. Anyway, what it means, supposed to mean, now we have definition by example. Well, then proof. I'll take this down there. That's why I picked it. Theta 4 from the right of all this junk. And so this is by this funny way of writing. Theta 5, theta 6, d coming to the right, d theta 4. And now it has to eat its way from the right. And deliberately, I chose 3 thetas on the left of the 4 and 2 on the right. So this only has to jump twice. So if this goes twice there to hit its partner, it gets 2 minus signs. So this is minus 1 squared. Theta 1, theta 2, theta 3, theta 5, theta 6. I have already done the derivative. And so that is different from that because this was the negative. And that's the positive. So it, obviously, right? It makes a difference whether you come from there and there, depending on how many times you have to jump. It really is just only a sign in the end, but you'll be very annoyed if your signs don't work out in the end. So it's just the sign means, oh, it's serious, right? In fact, this all started because we wanted the sign for this master. This is more or less it. You can, of course, also start to integrate. We don't need to integrate at this point. You can integrate all those variables. Later, maybe we'll integrate all those fields in the path integral approach, but then we'll come to the rules then. One thing is the complex conjugation. I haven't done the complex conjugation here, but our spinor fields are complex, but that's easy. You just introduce more symbols, so like complex, Grassmann, so for every theta that you had, you also introduce symbols theta 1 star, theta n star. And that's it. And then these anti-commute, now a bigger set. It's a 2n dimensional space. Counting kind of real And theta one, intercomputes with theta one star. And they among themselves and all of that. And the rules for complex conjugating, you just copy from what you know from ordinary complex numbers. So, for example, like theta star star is theta. Or yeah, except for one. If you have a product of thetas and you want to complex conjugate the whole product, then they want us to reverse the order. So if we have theta I, theta j, theta k, and so on, if you want to complex conjugate the whole thing, then it isn't star, 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 but it is the other way. And then theta k comes first, theta j, theta I, the other way around. Which doesn't differ much by the expression where you keep the order, could only be a minus sign. Maybe it's not even that. The reason why we want this, reason for this definition, if you have sort of a square of a variable, of a Grassmann variable, that's like the absolute value square. I can define this as to mean theta square, what you do with the complex numbers. And that object should be a real number. Let's give this a name A. So a real number satisfies A star is equal to A, right? So that's really what we want. So that it all looks familiar. And if I, so we want the A is this, and the A star is the theta star theta all star. If you just kept it the order, then we can do both ways. Then we have star star theta star, and that is theta nothing theta, and that is the negative of this. And then suddenly, like with this definition, like no, here, this is it does not change or reverse order, and that's not that would make A defined in this way imaginary. This is not what you want. So we define it in this way, that they reverse the order. This goes first, and then comes this. And that is A, and then it looks better. So we are happy with it. That's why we define it in this way. Yeah. If versus order, and that's why we do it. This was some funny math. Now we are ready for some very exciting topic like physics. It's Noether's theorem, but I'm introducing this with an example. So, with an example that does not use any machinery. Like, forget about the headline of this section. And I'll add it in later. Say we have a scalar field, real scalar field, satisfying the Klein-Gordon equation. Klein-Gordon equation, so that means we have d mu phi plus m squared phi, Klein-Gordon equation, I don't even remember. And two derivatives, both, I was writing the action, equals this. So that's what we have. And now comes a sequence of totally unmotivated steps. And that's the point of, that's my way of introducing the purpose, like why are we doing what we will be doing in a minute? Because you wouldn't guess all these steps. Now, multiply it by d mu phi. You ask why? That's no. D mu phi plus m squared phi. You just make sure that I'm not making any mistake. Now here, for some funny reasons, I want to pull out the d mu, and then I have this thing. But now this mu hits also the second phi, so I have to correct for it by subtracting d mu phi d mu phi. Right now it's okay again. All of this is equal to these two terms. Now I made it more complicated by having two terms. What else can we do? We can, here, this thing, for example. I also want to pull out this derivative, and the convenient thing is that I have the same factor. So I'm going to write this as 1/2 d mu phi squared. Does that make sense? So if I have like product rule, so the 2 comes down and then phi times phi product. Does it make sense? And now, since this was so successful, I'm going to do the same thing here because this and this is the same. So that part in the middle here is d mu phi with 1/2. And so since I don't want to get confused with all the indices, I'm going to relabel this as kappa. It's just they're contracted. Makes sense, right? So if I differentiate, I get once the first, and then another time the second. They're both the same. Against the 1/2, I get back this. So the minus sign is still there to remember. Now I have 3 terms: this, and this. The first one has the outer derivative d mu. The second d mu, the third d mu. I don't like that. I want them all the same. Here I don't want to mess with it. So this I'm going to write as 1/2 d mu. Well, that's wrong. So I have to put a has to be mu, right? So I put a delta mu in there, and suddenly it works. Right? The delta, that's this mu to mu, and that's what it's supposed to be. And here the same. So this is 1/2 d mu delta mu phi squared. And now, reading the whole thing, it's d mu inside the parentheses is this minus 1/2 delta mu d kappa phi, and then plus 1/2 delta mu phi m, another m somewhere, m squared phi squared equals 0. Did I make a mistake? I might have. It's I hope not. So what I've done is I've rewritten the equation of motion for our field. It now looks like this. But this is a nice way of writing it because it's a divergence of something. So this guy here has a mu index, and then something is, yeah, and it has a new index. The mu is contracted here and it has another hanging new index right there. So it's basically four different things. I can call this in here J mu, that's the upper, and then it has also an index mu downstairs. And then the equation is d mu j mu with this mu is equal to 0. And that's a continuity equation, right? Because I used the letter J. No, it's not because I used the letter J, but every divergence is a continuity equation. Why? Let's write the components. So J mu has a 0 component, which I call rho, and it has a vacuum component, which I call J, and then my derivative is, as always, by T gradient. So with the downstairs, it's the gradient with the plus sign. Then this equation means rho dot plus divergence of this 3 is equal to 0. And if I pick a volume, and integrate this equation over this volume, this is just ordinary three-dimensional space. It's not space-time, just this. So I have integral rho dot dv over v equals, say, bring this on the other side, so minus integral divergence j dv over v. And then here, that's easy, it's a time derivative, but this is a spatial integral, so I can actually just integrate and then differentiate. So this is the same as p by dt integral rho. You know, this is a function of x and t. And I'm integrating over the x in this volume. So the result is just a function of t, and I take the derivative. And that is by this equation equal to minus the integral. And even Gauss says, if you integrate over the entire volume all the divergences, you might as well just count what you have on the surface. Like the flux through the surface is the same. So it's integral over the surface of this volume, if it has one, and then j project onto the normal of the surface, and then all the way around. And you call this thing QV. It's a number that depends on time, and you call it the quantity of something inside the volume. Maybe we want to call it the charge or so. Something inside the volume, and all of this without the minus sign, you call, like, this is the definition, I dV. This is the current through a surface. Also depends on time, because you can have more or less going through. It doesn't depend on space because we integrate it over the fixed object. And then this equation says this. So if I have a volume, this is my volume V. No, this is the surface A, and here this is the volume, and I have some stuff. The density inside. And then, well, everywhere, not just inside. And then I have some current going outside, and then this holds. The change of the total quantity inside is equal to the current is stuff per time flowing through the boundary, and the minus sign means if something flows out, it gets less in the middle. So that's your the integral version of this equation written in time and space separated notation, basically. And if your volume say is, well, if nothing flows through that surface, then that's zero, and then the QV is constant. It could either be there is nothing flowing, or you choose your volume to be the entire universe, and then you just say it's the entire thing, so there's nothing leaking because there's nothing where it could leak into because you have by definition chosen everything. So then the Q is conserved. So that's why we like this equation. We do like the equation of motion too, but we like it also particularly in this form. You see, this equation is not in this form because the second one it's not the fourth derivative. So I had to go through these random steps to turn this equation into this. And whenever this holds, this holds. Well, this is a little bit of a funny thing. I multiplied it by this thing, but it's more or less equivalent. But yeah. So I like this because I can get these Q's. And now your question is, where is this charge coming from? What is that charge? You know, we had an equation, and suddenly we ended up with this object here, and it has a zero component. The zero component is this rho, right? So I just have an integral over the zero component of this thing, 0. It has another index mu. I don't know, it could be 0, 1, 2, 3. And if I integrate over all space, then this is suddenly conserved. Funny. Where's this coming from? Why these number of steps? So in this, the answer to this is Noether's here, 5.2, which does the same derivation, just more systematically, and it connects it to what's called a symmetry. The charge, the conserved charge, and this conserved current, we call this a conserved current that satisfies the continuity equation, we'll sloppily call the conserved current. Although it moves things around, it can be time dependent and everything, but we call a current that satisfies a conserved current just because it's shorter to say. So this comes about because apparently this equation or this theory has some kind of symmetry. So I'm going to give you two derivations of Noether's theorem. Noether's theorem is essentially an equation, or it's a formula that gives you a J from a symmetry. And the first derivation is very short, and I call it the no-nonsense derivation. No-nonsense derivation. And then I have a longer proper derivation. So here I'm doing physicist way and minimal stuff. So we have a Lagrangian that defines our theory, and that is a Lagrangian density. This is a phi of x derivatives and maybe x's. And now, say we have a transformation, like a variation or so. Like I'm going to use the notation from last week, the variation, but it's not the arbitrary variation that has to mention some terms, but whatever you want. So call it transformation. Infinite continuous transformation of phi parameterized by some epsilon. You see that it's already a small parameter, so it's continuous. You can plug in different epsilons such that for epsilon equals 0, the the transformation is the identity, yeah? Let's call it not identity, let's call it phi, it's not as well. I'm avoiding all the jargon. And so phi of x, I'm going to transform into phi of x. Oh, sorry, am I doing the? This is borderline nonsense, right? Well, if you like to keep it, this is totally nonsense. This goes in the second part. Like, why do we make it so complicated, right? There's a continuous transformation, like a deformation. Now you're supposed to keep it. It's not wrong. Consider a of phi, which now is phi plus delta phi. It's really what we did before. And if you want, you just stick in an epsilon, and if epsilon is equal to 0, then you have what you had before. Like this is where the sentence before was going. But yeah, like this. Now, what does this do to L? Delta L is now yes.
Do we fix any point, starting ending point? Or the
No.
the relation, okay.
No, like an example could be example. Well, let's just be honest and have an example. Didn't want it, but so phi goes to the phi plus a number. And now I'm using, I didn't want to write because I was just going to get rid of the epsilon, and now this is suddenly back, but now I've added an epsilon, which really means I'm changing phi everywhere. So there's nothing going to 0 anywhere. It's just really a change. It's a very little change, but it grows the field. I can also do something more fun. Another example, I multiply by this. What does that make? It's not changing phi by a constant, like not all the functions the values get bigger, but they get scaled. If phi of x at a certain position is already very large, it gets even bigger. If it is negative, it gets more negative. If 0, it stays 0. So this is a scaling. Or whatever. You can also add a derivative. Well, that's now funny because I have to soak up my indices. So I guess I have to take a directional derivative, and then you have this. Now you add something proportional to the derivative of the field. That is essentially translating your field, because if something like grows, and then you want, if it's a large derivative, you want to add more here. If it's a small, no derivative, you don't want to add anything. So what you end up after this is an infinitesimal shift of the thing. So I can do very fine things. I can just move it up and down. I can scale it. I can shift it in this way by adding derivatives. So it's all this, but it's just adding. My point is, it doesn't fall off. And it's not arbitrary. Like for the derivation of the equation of motion, we also had the variation. We called this then the variation of the field, and we inserted this, and we considered the change of the Lagrangian, the change of the action, and all of this. And then we said the action should be 0. The variation should be 0 for any variation, with that condition that it doesn't change at the boundary. Nothing like this here. It looks the same with the delta phi, but it's not a arbitrary thing. It is a specific transformation that I have in mind. These were examples. don't see any example, you only see the third one. But you have to have something specific here in mind, and it doesn't have to satisfy anything going to zero. Now, once we have this, we want to see what happens to this L. And yeah, I don't know, I was gonna, let's write the definition. So L of phi of x plus this extra bit, mu phi, what we had, plus mu delta phi of x, and then x doesn't get changed, it's a change phi. And then I subtract the L that we had before. And that's then the change, and I only want to keep linear in this phi. And if you don't like the counting of linear in phi, then you have to think of an epsilon in front and then expand it in terms of epsilon. Like we talked about this after the last lecture. And you just write this with an epsilon, and you take the derivative with respect to epsilon. Stick it in there, derivative of this with respect to epsilon, set epsilon to 0 at the end. Then you get exactly what we have defined here in this other fashion. And you can compute this. What this is. And if delta L is a Four divergence. You insert it and see what it is. And if it's a Four divergence, then so this means there exists a function f so that the delta L can be written in this way. For some f mu, which is a function of my phi and the derivatives and the axis if it wants to be. It's not the field strength for the vector field, it only has one index, it's just some function f for function. So if that's the case, then the transformation like delta phi, or really this act here, this thing, the transformation phi to phi of x going to phi of x, delta phi of x is called a symmetry. And now let's be specific of the theory defined by this L, by the given L. I should be given on this L. And if that happens for your transformation that you've chosen, and the one that I'm going to choose in a minute to rederive this, is where I do this with the derivative. How did my sentence start? For this theory, the Lagrangian for this, where pick this as an example, it will be a Four divergence, and then this is a symmetry. And if that's the case, then the following works. This delta L can always so delta using, it's important, using the equations of motion, delta L can always be written as a Four divergence. So note that here I haven't used the equation of motion. I have just said come up with the transformation, plug it into your Lagrangian, massage it, and see whether or not it is for divergence. I never said, okay, go ahead and use the equations of motion. And I forbid this. Just insert it and see if it is like that. It could be zero, right? If it's zero, it's even better because zero is also the divergence of some constant or so, or of zero itself. That works too. But now, a second way of thinking about delta L is to use the equation of motion. And when I use the equation of motion, then the delta L is always for divergence. Let's see this. So delta L. Now I do my Taylor expansion. Is dl by d phi, the first argument, delta phi, plus dl by d, and now what index do we use? Mu phi, delta d, mu delta phi. And the x doesn't change. So that's already it. I've just Taylor expanded it. And you would probably do the same thing when not using the equation of motion. That will probably also be the first step to find this sum. But now I can use the equation of motion. What is it? This thing is equal to d mu dl d by d mu phi, right? By equations of motion. Remember right? You have to, I can also write them again here, but this will convince you even more because I've written it. So this is the Lagrangian equation. And that's really nice because now you have the derivative on this thing, which is exactly that thing. And here the derivative is on the back, so it's a total derivative. Bam, bam. d mu of dl d by d mu phi delta phi. Oh, so it is. Upon using the equations of motion, it is always this forward divergence. And now we can put both equations together. D mu f mu is your delta L, and here delta phi is a symmetry, not using the equation of motion, and here I write d by d mu of dl d mu phi delta phi, and here equations of motion. And if you have now both, you have the equation of motion satisfied and delta being a symmetry with the definition we just said, you can of course read from here to here, put this f underneath the, so you get d mu of dl d mu phi delta phi minus f mu equals 0. There's your first no nonsense version of Noether's theorem. You have to give yourself a theory under consideration. You have to give yourself a transformation, and the transformation has to satisfy has to be a symmetry, and that means it has to turn delta L into a forward divergence without using the equation of motion. And then this combination is divergence free. So then you call that object your current. And now we will try this out. If that works for the Klein-Gordon field.
Can I ask?
anytime.
I'm not fully sure that I understand the statement, because we started with saying how find a transformation such that your variation becomes a divergence.
Yes.
And then we can set, but we can use the equation of motion and then write the variation always as a divergence.
Right,
Those are not the same statements. Those are
no,
very different statements.
yes,
And the second one seems very strong to me. And so why is this true for all transformations that you can write the variation in terms of for divergence?
Because the equations of motion were so strong, we derived them. I can already see you are the one who wants the long derivation, and then it makes it all be clear. And I feel the same. I feel like, oh, this is something weird going on. You know what? Why is this not? Yeah, but as a preview, the equations of motion were derived for arbitraries. And then we had so delta phi with here inside the equation of motion. This is the variation of the action in an integral. And then we had a surface term, mu, and then the delta phi inside with stuff. So this, if you remember last week. And then we said, well, well, not arbitrary, delta phi equals 0 on things on the boundary and otherwise arbitrary. But then this thing set the second one to 0, right? So we didn't see this. And then we concluded, oh, okay, if this is arbitrary, then the equation, then this needs to be 0. So if this is arbitrary, then this needs to be 0. And now I'm using, this is 0. I'm using the equation of motions. I said this here. So this doesn't have to be so strong anymore. This can be any random transformation like this. And then this is anyway gone because of the equation of motion. And what you're left with is this. This is your short. Because everything that isn't the divergence, that doesn't turn into a surface term under this action integral, is killed by the equation of motion. So everything that is left is that. And this is just the preview for tomorrow. I'll write this with numbers there.
Sorry, but this only means that this term has to vanish at the what's the
Which term?
the last term doesn't have to vanish at the overall surface, right? So such that the variation of S vanishes. In this case,
Right.
or does it?
Depending on what you're talking about. If you're talking about the derivation of the equation of motion, then you want this gone. And this goes by saying the variation on the surface is 0. And then you can conclude, okay, this equals 0 is the equation of motion. Now I'm using the equation of motion, then that's gone. And this isn't gone any longer because my delta phi is whatever the delta phi is, and it's not 0 on any boundary. It really, I care about the boundary. This is where this thing where it flows in and out.
Yes. So if we go the other way around, we could conclude that if the equations of motion, so this is our assumption, right? The equations of motion vanish. So they are just 0. And
Yes.
then we can conclude, if we want the variation of S to vanish, that this term on the boundary has to be 0. So that's,
Yeah, if you want delta S to be 0, then we have to ask this has to vanish. But I'm not asking this. Not delta S equals 0. I'm setting this equal to the other way of writing it. Basically.
okay, I guess that's C2.
Yes, you'll see tomorrow, exactly. And I wanted to keep it very, very simple, in the first round. Um, Somehow it's simple, but then it's also confusing. And I was very long confused if, don't I do twice the same thing? Delta L equals a four divergence, and then I show delta L equals a four divergence. So, do I get anything? It couldn't it be that this is literally zero all the time? The same four divergence here and there. That's what I, in the beginning, found very unsatisfactory. But then, if you remember that on one side, that's why I'm writing this, you don't use the equation of motion, you just use the symmetry, and the other, then it can't be the same thing. You do different things. Here you just do a variation, from here to here you do a variation, which has a certain property, so it restricts your delta phi, and here, you just say that the equation of motion satisfies. This is a property for phi. This is a condition on phi. This is a condition on delta phi. So now it's here, example. The L is a half d phi minus 1/2 n squared phi squared. And I am using phi of x should go to phi of x plus, say, sign doesn't matter, a mu b mu phi of x. Why not? It's something I propose, and now we have to see whether this makes any sense at all, if this is a symmetry or not. Okay, easy. Delta L is so I have to insert this thing and expand basically in this A, so I can have it once there or there. So I get 2, and I have a d mu phi, d mu, and then this thing inside. So this is now called an A mu d mu phi. All right, this is the derivation of this first term. Can happen here, can happen there. Same though, who's gone? But the 2 was there, that won't happen. And then minus m squared phi, and here, let's keep it in mu, I guess. Keep it in mu, what do you want? Mu phi of x, all of x. And now we have to work and see if this can be turned into a 4 divergence. I guess this is where, in this naive, simple-minded approach, the work goes in. Can we actually see that this is the? And now the steps will be very similar to what I did in the beginning, like these unmotivated things. Here, for example, we pull out the d in the same way we did before. So this is a half a mu b mu phi squared. And here I'm pulling this out. So this is a half a mu d mu phi mu phi. In the end, it had to be very similar. I mean, the work kind of stays the same. It's just a bit more motivated. And why this is the right thing to consider, it will also be motivated. This is a translation. Let's say now, this transformation I'm considering here is a translation in space. The field is shifted, and the conserved charge corresponding to shift is the
Momentum.
The momentum, exactly. If you push it into space, it's really the spatial momentum. If you have a push in time, then you have the sort of zero component of the momentum, that's the energy. So what we find is the energy momentum, as conserved charges. So this is the shift in x and t. This worked well, so we have maybe I want to call this though mu. So I'm writing mu here because this is the same. So then we have a half. No, this can't be mu, this is going to be the kappa. You know, the current will be this very same that we had before, and then minus m squared half phi squared. So this is what it is. The variation is indeed the four divergence, and if you don't like this outsum, then we have a mu. So that's now it's really now this is what it is. This is phi mu. This thing is f mu. And funny, it is the Lagrangian, right? It happens to be the Lagrangian in this case. Strange. It's not strange, really. If this was a little bit nonsense, then I would say, look, the change of my transformation here of the field phi was a derivative with this as a parameter. And my Lagrangian changes in just the same way in a mu, d mu of itself, right? What we've just found is delta L is a mu d mu L. Like it does the same thing as the field does. So that's why it's a shift. You shift the field, the Lagrangian shifts. Oh, surprise. And now we use the formula. This was the work. This was the work part. We don't have to start completely guessing. This was motivated by it simulates the translation, and then we had a hope there was a further divergence. Then we did the work to find the f. Once we have the f, it's applying the formula. We just need to do this. So our current j mu really is this dl by d mu phi times the variation that we've used minus the f. And the variation is easy. It's just d mu. The 2 goes away again, so it's d mu phi. That's yeah. And the variation of the field is a. Now I can't write mu as well. I have to write a different letter. So mu d mu phi. And that's it. And now minus this a mu a half d kappa phi d kappa phi minus m squared half phi squared. That's the current. And let's see if this makes sense and is the same that we had here. I didn't erase it on purpose. The difference between what we have on this side of the board and on this board and there is that here we see this A in there. So let's kind of pull out the A. So A mu comes out, and really I want, I want it A mu out, and I have a d mu phi, and here because it's a mu, I have to insert a delta mu, and then d kappa phi minus m squared half phi. Nope, the half is there. M squared phi. Boom, boom. And now the current that we have with this procedure is this parameter of my transformation times that thing, but this was arbitrary, right? It could be, I could have chosen anything. So I could, for example, now choose a mu to be 1, 0, 0, 0, just this first component. Then we would have obtained this side with this being 0, because it's just the first. We could have chosen in next go this one, then we would have gotten everything here, no A, but here 1 and 1, and then 3 and so 2 and 3. So with this one computation, we have gotten 4 results for all the different values of mu. So what this really means that this is conserved for any mu. So we can define this as what we had up here with the 2 ABCs, and now it's very simple. So d mu j mu is current for any mu. The one with the 0 here is, well, the flow of the energy, and the other ones is the flow of the momentum. It's complicated, right? There's a momentum, it's a vector, and then the momentum can also flow. You transport the momentum. The momentum itself is the 0th component of the current. So well, yeah, then this is the last example, I suppose.
I have one question to before you fill in all of it.
Yes.
We just said that the variation of L is 0 for that tree.
The variation of L
Because otherwise I don't.
is 0. The variation of L is this. This is the F. The F is what's in these parentheses here, the whole thing in brackets here. And that's what I inserted here. The L does vary.
I wasn't quite as fast as you in recognizing how that is F.
Well, I gave myself the L, the theory, and then this transformation, and then we inserted this into L. No usual equation of motion, just pulling derivatives around. And then I was able to pull out the derivative d mu, and then everything that the d mu hits is F. I'm not looking anywhere else. I really try not to look anywhere else. I'm just saying, oh, it's a total. There's nothing else coming. There's no plus blah blah blah. Everything's inside these brackets. D mu hits the whole thing, and then the whole thing's. I'm just calling this F. And then I know F itself is not the current, because this is just how it varies under the transformation. But I have to add this piece. This is how it always changes by use of the equation of motion. And then this minus the F. Still not looking, and then and now I look if it's the same. And then I haven't even compared, I don't dare, but it seems to be the right thing. And so this is now a set of 4 currents. And what people just give this whole thing a name. I'm only going to write 2 more lines. This object there with, say, raised indices. So let's pull this up. And then the minus a half eta mu d kappa phi d kappa phi minus m squared phi. This current. Instead of writing as J, they write it as T mu, and then the mu is the one that counts, and this is called the
stress tensor?
Yes, you can call it the stress tensor, or the same word is the energy momentum tensor. And there, the momentum. So it's a tensor, because this is not energy and it's not momentum, it's basically everything. It's where the energy sits and how the energy flows and where the momentum sits and the momentum flows. And the charges, always the charges Q is always integral rho 0 e to the x. So we have to pick the 0th component of this current. So this means we have to take T0 and integrate it. But then you have a choice which one to take. And you can take the 0th one, and that's your energy, called H, for Hamilton's sake. And then you have integral T0, the other ones, and that's the momentum, so energy momentum. These objects are the current. So the first one being 0 is the density of the stuff. T0 is the density, so T0, that 0 is the density of the energy, and this is the density of the momentum components. Integrated is then the total momentum. Yes. So that was just to give these things a meaning and connecting it to what you know. Before we do examples and write and find for all the theories, all the charges, the question that you have is, what's the F in general? It always seems to be, it seems to be something that comes as a surprise, right? You do the variation and then you have to compute and you have to massage it and then find the F. The other derivation that we're going to do tomorrow with all the formalism, where maybe all more details become clear, will actually give us an expression for the F in general. So we don't have to do this case by case. But sometimes this is still useful if you work in a concrete example and you try something out and then so it wasn't a waste, I think. But tomorrow we'll derive the form of this thing in general with a more complicated one, and then we do the examples. That's the plan. Questions?
Excuse me. Can you hear me?
I can hear you well.
Okay. I have a question. How do I know that something is a symmetry, like a del phi? Because I thought we said it is a symmetry if we can write it as this del mu f mu, but then we argumented the other way around that we can write it like that when del phi is a symmetry. And what makes del phi a symmetry?
What makes delta phi a symmetry? It just shouldn't change. So very broadly and non-precise speaking, it shouldn't change your Lagrangian, right? Where's our Lagrangian? Gone. Let's write this, the complex one. So now you just stare at it for a second and you see, oh, wait a minute, there's no reference to the origin of the universe. There's no X in there. There's no particular point. Nothing singles out. So if I move X, if I say X equals 0 is here or there, it doesn't matter. So I'm just looking at it and I see pushing everything over shouldn't change much. Shouldn't change the theory. So then I need to figure out, and we'll figure out, how to write the pushing in X as a transformation of the phi. And that is, as I tried to explain with my picture, adding to the field its derivative. That is pushing it. I'll explain tomorrow how you see this. But then from this iteration, from looking, oh, there's no origin in there, there's no explicit reference to a certain point, I should be able to push it. Then I write down what the pushing is, and then I insert it, and then I see, aha, I'm not going to give up. I'm going to work this so long that it is a 4 divergence, because I know it has to work in this case. And I wrote the complex one because I wanted you to look at it and think about another symmetry. What else can you do to the phi? It doesn't work in the real case, but in the complex. What can you do to the phi to keep it basically what it is. Complex, yes.
Rotate,
Rotate how?
like e to the I something.
Exactly, so if we change phi of x to phi of x, but multiplied by e to the I something, like epsilon or so, then the complex one will change into e to the minus I something. And since they always come in pairs, and the derivative doesn't bother this factor, so then it goes away. So we have, but just by look, this is how it works. You look at the theory, and then you kind of see, you're supposed to see the symmetries. Then there are theories with the hidden symmetries. Then you look at it and you don't see it, and you call them hidden symmetries. Like the hydrogen atom has a four-dimensional rotational symmetry, you wouldn't guess it. But you know, the obvious ones, you just look and see it, and then you write it down and derive the F and then the conserved current. Often in practice, you also design your theory, your Lagrangian, such that it has the symmetry. Like, for example, we wanted the translation symmetry. Translation is just part of the Lorentz transformations. That's wrong. I'm sorry. I take this okay. So I cancel the last sentence. Translate. Let's say rotations. We can also rotate the coordinates, like my coordinate system. Why? Because we wanted it. I can boost it because we set it up that it is Lorentz invariant. So of course it's a symmetry. The translations is extra. We didn't put this in, but we didn't talk about it. So it was a long answer. Did I happen to answer your question?
Yeah, thanks.
Lucky, yes. And let's reconvene tomorrow.